Hello, everyone. So today we're going to discuss the paper called "What Can Human Sketches Do for Object Detection?" This paper was presented at a CVPR 2023 and it was accepted. So the objective of the paper is to explore the innate properties of human sketches for the task of image retrieval. And the paper cultivates the expressiveness of sketches for the task of object detection, and the end result is a sketch-enabled detection framework that detects based on what you sketch. So the model made in a way that it does expected testing, so like it works in a zero-shot setting, and it does not require additional bounding boxes and class labels for supervised and weakly supervised training. And to enable the generalization, the model utilizes CLIP and SBIR to bridge the sketch photo gap. So on a high level, the model works as follows. So you can either prompt zebra eating grass. The model will detect that exact zebra, which is eating grass on the photo. Or you can also prompt a specific object, like the head of a zebra, and the model will also detect only that specific part on the photo, like here, the head of a zebra, meaning that it's actually an instance-aware and part, it's enabled with instance-aware and part-aware detection. And so, in its core, okay. In its core, the model works as follows. Oh, sorry. The framework consists of two key modules, object detection and the sketch-based image retrieval. And for the object detection, the model utilizes the faster RCNN. And I will not dig deep into faster RCNN, but briefly, the model produces a feature map using the feature map using the encoder of faster RCNN, which is either a VGG or a ResNet, and using that feature map, an RPN generates rectangular boxes, like a set of boxes, and an object and scalar, which gives the information on whether the box contains an object or not. And finally, the proposed regions are funneled into a pooling layer using ROI pooling, and then followed by a fully connected layer to get the feature patch, which is then streamlined into corresponding classification head and the regression head. So the baseline SBIR framework works as follows. So given a sketch photo pair, SP, the SBIR model extracts the corresponding feature maps from both sketch and photo. And then for training, the cosine distance to a sketch anchor is applied using the negative photo and a positive photo. The cosine distance for a negative photo should increase while the other one should decrease. And training is done via the triplet loss. And to extend the SBIR across multiple categories, SBIR is trained using the same triplets, and the cross entropy loss is applied. So for a weakly supervised detection, we have the same model in the beginning, but with the fact that the RPN now is not trained. Rather, it uses the pre-trained weights or either heuristic search or edge boxes. and the resulting patches are then directed into a classification head, which uses softmax across C plus one categories, and the detection head, and their results are combined together. They're combined together, and so this training is done using the cross entropy loss. And since weakly supervised detection model only uses image level class labels, and they fail to naively refine the proposals, the model also extends to k-step refinement to predict the refined class score for each RY. And the refinement classifier is supervised via pseudo score labels. So to stitch together the object localization and query sketch, the fixed set of classifiers, the fixed set classifiers in WSOD are replaced with the scalable open set prototype learning, and each prediction head from WSOD is replaced with the is modified to compute the embedding vectors. So here, this is the framework of WSOD, and now it computes the embedding vector. And so the sketch encoder is attached to compute the support set of features and the learned catch-all background embedding. So the classification and detection score are computed by multiplying the embedding vectors with the support set of sketch features. So these are the support set with sketch features, and they are multiplied by the embedding vectors. And so the training is also enhanced by the photo encoder, which basically accepts the features from region proposals, and also the cropped region of the original photo, and computes an L1 loss on top of that. So, and to train the object detection using SBIR with high generalization and open vocab capabilities, the prompt learning using the CLIP or SBIR is used. So since CLIP consists of an image and text encoder, it can highly generalize in a zero-shot manner across multiple tasks and datasets. So for prompt learning, a set of learnable vectors for sketch and for photo are injected in the first layer of CLIP to learn the downstream sketch and photo distribution. And prompting CLIP preserves the desired generalization ability, since the knowledge learned by CLIP is distilled into prompts, weights, and the VIT is kept frozen at this time. So these are the results obtained by comparing the proposed model to the SOTA in SOD and WSOD detectors. So SOD means supervised object detection, and WSOD is weakly supervised object detection, and EWSOD is the class that is trained specifically only on SBIR dataset. Okay. So, and as you can see that the SOD, it outperforms the W, and it even further further outperforms the EWSOD uh, by nearly 5%. But even with that, the proposed model is trained in a setting of EWSOD, and it still outperforms the top SOD models. Yeah, it still outperforms the top SOD models. So uh, that's it for me.